Okay, so let's go ahead and do this next wonderful piece, which is optimization. This is 4.7. And so optimization is actually really, really cool. It's used a lot in business and things like that. And so these are going to be practical, real-life problems that can be tough. So here's our first example that we're going to do. And it's a farmer has 2,400 feet of fencing and wants to fence off a rectangle field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so since he wants it rectangular, they've kind of restricted the way it looks. One day that'll be a straight line. And so we have this rectangle that we need to build, right? And so here's the rectangle that they tell us. This is the river, right? This is our river. And so they say that he has 2,400 feet of fencing. And so the way I'm going to do it is I'm going to say, all right, this is X, and we'll call this side Y, okay? So that long side is Y. And so I know that Y plus X should equal my 2,400 feet of fencing. And then Y plus 2X is equal to 2,400 feet of fencing. So then Y is equal to 2,400 feet of fencing minus 2X, right? The key to this problem is, that's the perimeter. The key to this problem is that we are looking to find the largest area. And so the equation that we should use with this is area. And so going with area of a rectangle, isn't area of a rectangle X times Y, right? But in solving for the perimeter piece, we have a relationship with Y to X. And so I'm going to change that to be the area is X times 2,400 minus 2X. And so I'm going to distribute, and my area is going to be 2,400 X minus 2X squared. And remember, since we want to maximize the area, we want to get the largest area, in order to be able to find max and mins, what we need to do is take the derivative. And so I'm going to take the derivative of the area. So that's going to give me 2,400 minus 4X. Well, now that we have 2,400 minus 4X, we need to set that equal to 0. And so 2,400 minus 4X is equal to 0, because that's going to be able to tell us of a critical number. And so we're going to get negative 4X is equal to a negative 2,400. X is equal to 2,400 divided by 4. And so X is equal to 600. Now, when doing optimization problems, we always have to test this critical number. And so we're going to test it. And this is 600. And so we're going to test the derivative. And to the left of 600, if I used 500, 4 times 500 would give me 2,000. So 2,400 minus 2,000 would give me a positive number. And then if I plug in a number bigger than 600, let's say 700, that's going to give me a negative. So what I see is that this is a local maximum at 600. Now, the problem, though, isn't asking for where it occurs. It's asking for, and this is important for us to see, it's asking for what are the dimensions. So we want to know the dimensions of this thing. So we know that our width is 600, right? Our width is going to be 600, but our length, and this should be in feet, right? Let's make sure that we have the right units. Our our length then is going to be 2400 minus 2x. So our length is going to be 2400 minus 2x. So then 2400 minus 2 times 600 is going to give us 2400 minus 1200, or 1200 feet of fence. So our dimensions are 600 in width feet and 1200 feet in length. And the reason it's optimized is because we see from the derivative that we in fact do have a maximum. Are you guys okay with that for this first example? All right. We got a few people back. Cool. Okay, so let's look at the next problem. This is a closed cylindrical can. And so a closed cylindrical can is like a soda can, right? So we have this soda can that we're going to be able to go after. And so let's see what the problem says. It says a closed cylindrical can is to hold 1 liter or 1,000 cubic centimeters of liquid. How should we choose the height and radius to minimize the amount of material needed to manufacture this can? Well, we can see that this is a practical problem because Coca-Cola and Pepsi and all these soda companies, they want to get something to hold a certain amount of liquid, but they want to spend the least amount of money on the material to build those things. So let's go ahead and see what we need for this problem. So let's let h equal our height, and that's going to be in centimeters, right? And then let's let r equal the radius, right? Because it's a cylindrical thing, and so it's got a circle to it. There's 2 formulas that we're going to need, and these are formulas that you guys should know. We should know the surface area of a cylinder, and I totally know you guys all know it. So since you guys all know it, I'm just going to write it down. And the volume, and volume is pi r squared h, right? Those are the 2 formulas that we're going to need. And so this problem is asking for the amount of material that's needed to manufacture the can. So since it's the material that we're going after, isn't that the surface area? So what we're going to be looking to manipulate is this formula here, because it's asking for material of the can. Does that make sense to you guys? Okay, cool. Now, but we do have some information in terms of volume. So we know that pi r squared h is supposed to equal 1,000 centimeters cubed. And that's given to us by the 1 liter of liquid being held. And so what I'm going to do is I could solve for r, or I could solve for h. And for me, I think it's going to be easier to solve for h because I don't want to deal with square roots. So what I'm going to do is I'm going to go, all right, h equals 1,000 divided by pi r squared. And now what I'm going to do is I'm going to use this substitution for h into my surface area equation. So then I'm going to get the surface area is equal to 2 pi r squared plus 2 pi r, but my h, instead of having h, I'm going to make it 1,000 over pi r squared. Are we okay with that? Just a simple substitution of the green highlighted equation that I gave, right? Okay, so then in cleaning that up, I'm going to get the surface area is equal to 2 pi r squared plus 2,000 over r. Are we okay with that? Okay, now that we have this piece and we've simplified it as much as possible, we can take the derivative. And so when we take the derivative of this thing, I'm going to get S prime, the surface area's derivative is going to be 4 pi r minus 2,000 r squared. Now, let me know if you can get that derivative on your own. If you need my help, I can show some side work for you guys. Just let me know. Would you guys like me to show the side work on that at all? Can you show? Sure. I'll do that. Okay, so 2 pi r squared plus 2,000 over r, I'm going to rewrite that to be 2 pi r squared plus 2,000 r to the negative 1 power. So by the power rule, this 2 here is going to come down front, so I'm going to get 2 times 2 r squared minus 1. And then over here, that negative 1 is going to come down, so negative 1 times 2,000 r to the negative 1 minus 1, right? That's the power rule. And so what that's going to give me is 4 pi r minus 2,000 r to the negative 2. Well, that's going to become 4 pi r minus 2,000 over r squared. Does that help? Okay, so those are all the steps. Like I said, I want you guys asking me questions so I can demonstrate the work that you need, because like you can see, I can do it in one step, but I don't want to take that for granted with you guys. Be honest with me and we'll do well together. Okay, can I erase that though so that I can continue the work? Okay, cool. All right, now from here what I'm going to do is I'm going to have common denominators. So in making the common denominator, I'm going to get 4 pi r cubed minus 2,000 over r squared. Are there any questions on that piece? Do you need me to show how I got that? Or anybody? No one? Just making sure. Okay, so then from here what I'm going to do now is I can go ahead and test this thing. So we can see the only real issue that we have is when r is 0. So we'll avoid r equaling 0. But we can check when the numerator is going to be 0. So I'm going to go, all right, 4 pi r cubed minus 2,000 is equal to 0. So then 4 pi r cubed is equal to 2,000. Pi r cubed is equal to 500. And then the cube root is equal to 500 over pi. And then I'm going to take the cube root of that. So I'm going to get r is equal to the cube root of 500 over pi. Now that is my critical number. So then that means I need to test that, right? So when I test it, and there's 0 too, but that doesn't matter. That's just going to be a value of 0, right? If we don't have it, if we don't have a radius, then we don't have a cam. So that's just common sense. All right, so now plugging into this thing some number that's smaller than the cube root of 500 divided by pi. So we could plug in 1, right? So 4 times pi times 1 is going to give me like, I don't know, right around 12 something. So 12 minus 2,000 is going to give me a negative number. And then if I pick a number bigger than that, let's say I picked, let's just be blatant because we can pick any number we want. Let's say I picked 1,000,000, and 1,000,000 cubed is going to be something really, really big. So we see that this is going to be positive, right? So what does that tell me about that number? What is that number? What does the derivative tell us when it goes from negative to positive, guys? We have a local minimum, correct? So we have a local minimum at that number. Now, let's look at what the question said. How should we choose the height and radius to minimize the amount of material? Well, we now have the radius, right? The radius is the cube root of 500 over pi. We need to go get the height. And we can get the height from here, right? So the height is going to be 1,000 over pi, the cube root of 500 over pi, that quantity squared. And we could clean that up if you guys wanted to. I don't mind. Do you want me to clean it up, or is it okay if I leave it like that? I mean, at that point, it's just some algebra, but I don't mind. You guys want me to clean it up? Okay. All right, so to clean this thing up, I appreciate you guys so much. You've made me sad. But okay, it's cool. I'm going to get 1,000 over, and then I'm going to get pi, and then what's inside, I'm going to rewrite it so it looks like this. Cubed, not cubed. It's going to be 500 to the 1/3 power over pi to the 1/3 power, and then squared, which will be 1,000 over pi to the 500 to the 2/3 over pi to the 2/3. And then pi to the 2/3 and pi to the 2/3, doesn't that become pi to the 1/3? So I'm going to get 1,000 pi to the 1/3 power, 500 to the 2/3 power. And now I'm going to do some tricks. I'm going to go 2 times 500 over pi to the 1/3. And this is 500 to the 2/3. So that's going to give me 2 500 to the 1/3 power over pi to the 1/3 power. And that is my height. Oh, terrible. Cut that. Okay, does that make sense, guys? It's just power rules, right? But now we have our two answers. There's our height. There is our radius. So we're good to go. We were able to optimize the can. All right, this next problem, please know it well. It's a problem that I really, really like. So, I don't know, star it, fall in love with it, do what you gotta do. But it's a problem that I really enjoy and think is good. So what this problem is saying is find the area of the rectangle that can be inscribed in a circle of radius 4. So, and it's a semicircle of radius 4. So we're going to take the semicircle to be the top half, okay? So that's going to tell me it's going to look something like this. So this is 4, this is 4, this is negative 4, right? And since it's a circle, we know that the equation of the circle is x squared plus y squared is equal to 16, right? And since we're taking the upper half, I can make this equation to be y is equal to the square root of 16 minus x squared. Do you guys agree with that? And since we want to find the largest inscribed rectangle, I'm going to go like this. And I'm going to go like this. And then I'm going to go like this. Right? That is the largest inscribed rectangle on the positive side of this half circle, right? Semicircle. Now, because of this, how far is it from here to here? Isn't that some x distance that we don't know? Right? And so I also know then that from here to here has to be some 2x distance, right? Now, what's cool is where this thing intersects, this line intersects, this corner of the rectangle intersects the half circle, that is the height of that circle. So isn't that this as a height, right? It's the square root of 16 minus x squared. Right? So now something cool's happened. We have a length of 2x for the rectangle, and we know we have a height of radical 16 minus x squared. Right? And so the area of the rectangle, because they're trying to get us again in this problem, they're going after find the area that's largest. That means we're obviously going to have to take a derivative. And so the area of a rectangle isn't that length times width. So we're going to get 2x times the root of 16 minus x squared. Right? And man, how do you guys want me to do this? Do you want me to do it as a product, or do you want me to show you a trick to do it in an easier way? The trick, okay. The trick is cool. Some people might get lost, and if you get lost, go ahead and try to do it with the product rule, and we'll go like that. So if we were to do the trick, what would happen is I'm going to put the 2x into my radical, and when it goes in, I have to square it. So I'm going to get 4x squared times 16 minus x squared. Right? Because anything that gets put into the root gets squared. And then when I distribute, I'm going to get the square root of 64x squared minus 4x to the fourth. Okay? And when I take the derivative of this thing, I'm going to take the derivative of the outside. So I'm going to get a 2. And then that guy's going to come down as 64x squared minus 4x to the fourth. And on top, I'm going to get 128x minus 16x to the third. Are you guys following that? Okay, cool. Okay, and then from there, I'm going to factor out some things that they have common. So I'm going to go, I think 16 can come out. So I'm going to get 16x, and that's going to give me 8 minus x squared for the numerator, and on top, or on the denominator, I'm now going to be able to pull out some stuff. I can pull out a 4 and an x squared, so that's going to give me 2x being pulled out, and what's left on the inside is going to be 16 minus x squared. Okay? Oh, I need another parenthesis. Okay. So that's going to give me 16x 8 minus x squared over 4x square root of 16 minus x squared. That's my a prime. And so a prime is going to be equal to 4 8 minus x squared over the square root of 16 minus x squared. Well, where can this thing be 0? Is going to happen where 8 minus x squared is equal to 0, correct? As long as that's not 4 or negative 4, we're okay. So I'm going to test that. So 8 minus x squared is equal to 0. So negative x squared is equal to a negative 8. X squared is equal to 8. So x is equal to plus or minus 2 radical 2, correct? So that's giving me the 2x coordinates, and that makes sense because we should have one on the positive side, we should have one on the negative side. And so what we're going to do is we're going to test that. So here is negative 2 radical 2. Here is positive 2 radical 2. And let's pick some values. So if x was 0 for the derivative, do we get a positive or a negative number? It looks like we'll get a positive number in there, correct? Now, if we pick a number that's bigger than 2 radical 2, what is 2 radical 2? 1.7 times 2. Let's say we picked 2 radical 2. So I'm just trying to do the math. Let's say I picked 3 as a number. So if I pick 3, the denominator is going to be positive. The numerator would be negative, so that's negative. And so over here, we're going to get the same thing. So we get negative, positive, negative. And so what does this tell me? If I look at the right corner, and that's really the one that matters, doesn't this give me a local maximum? If we looked at the right corner, it would look like a local minimum, but that is just because of symmetry issues. When you're doing these problems, the only corner that you're going to look at is you're going to always look at the right corner, okay? You're going to look at the right corner. So you don't really have to worry about this other value. Does that make sense? And since we've shown this to be a local maximum, we have found what it would be. Now, this problem, if we really pay attention to it, it's saying find the area of the largest rectangle. So isn't it asking us to find out what both x and y are? So we know x is 2 radical 2. So then to get y, I'm going to have to go square root of 16 minus 2 radical 2 squared. And that's going to give me y is equal to 16 minus 4 times 2 is 8. So y is equal to the square root of 8, or y is equal to 2 radical 2. And since it's saying find the area, we need to multiply those two guys, right? So the area for the max area would be 2 radical 2 times 2 radical 2, which is 8. Okay? So we do have to read and see what the problem is asking for. And the largest area rectangle that we can find that's inscribed in this has an area of 8 units, whatever those units are, right? And they should be squared. Does that make sense to everybody? Okay. I'd leave it to you guys to be able to do it by the product rule. But if you need my help with that, I can also do it. Like I can just work it out and do it for you guys and send it to you. All right, let's do the next problem. And the next problem says to find two positive numbers, right? We're looking for two positive numbers whose product is 100 and whose sum is a minimum. So we know that we're trying to get x times y has to be 100, right? We have two numbers, x and y. And we want to find their sum to be a minimum, right? So I want to write everything in terms of one variable. And so what I'm going to do is I'm going to solve this x times y problem and solve for y. So from here, doesn't this make sense that then y would be equal to 100 divided by x? Right? Because we for sure know that two positive numbers, they're going to multiply to be 100. So then the 100 divided by the other number will give us our other number. So from here then, I know, and I'm going to show you, I'll go x times 100 divided by x. That is in fact 100, right? So we know that our multiplication of x and y is still 100. Okay, now the problem says to us though, we want a sum that is a minimum. So if we're doing a sum, that's an addition. So I'm going to go f of x is equal to the x plus the y, but my y we're going to substitute as 100 over x. And we're trying to make this thing a minimum. So if we're trying to make it a minimum, we need it to be whatever the critical number, it has to go from negative to positive, correct? That is what will make a local min. Okay, so then that means when we take the derivative of this thing, we should get some sort of min. So I'm going to get 1 minus 100 over x squared. That's the derivative. See if you can confirm that. Does anyone need me to show how I got this? No? Okay. So then from here, what I'm going to do is I'm going to find a common denominator. So I'm going to get x squared minus 100 over x squared is my derivative. And then to find this critical number, we're going to set the numerator equal to 0. So I'm going to go x squared minus 100 is equal to 0. So then x squared is equal to 100. So x is equal to plus or minus 10. Do I care about the negative number though? No. And the reason I don't is because we're in the positive world, so we only care about 10. So that means I'm going to test the derivative. Oops. I'm going to test the derivative at 10. So in the derivative, if I plug in a 9, I'm going to get a negative number over a positive number. That's going to give me a negative. If I plug a number like 11 in, I'm going to get a positive number over a positive number, which will give me a positive. And isn't this in fact showing our local min? Now, we know they want you to find two positive numbers. So we know one of the numbers is 10, that's x. So x is 10. What is y? It's also 10. Right? And we can get that because we see the substitution y is equal to 100 over x. So it's 100 divided by 10 is 10. And so this is my solution. So what do you guys think? Is this that bad? Why didn't you put the negative 10 on the number line? Oh, I thought I addressed that, but I'll do it for you just so you know. It's asking for positive numbers. And so since we only care about positive numbers, that negative 10 becomes irrelevant. Are you good with that? Okay, cool. Cool. All right. Do you guys want to try this problem? It's very similar to the radius of 4 problem. Or do you guys just want me to go through it? All right. That's fine. No problem. All right. So you have to be able to graph, right? But that isn't too bad. So when we do this problem, I know it's going to look like this. And we're trying to, again, find the two vertices. And so there to there to there, right? This height right here is occurring at 8 minus x squared. We know that this is x and this is x. So we know that this whole thing is 2x. And we know our height is 8 minus x squared, correct? All right, so to do this problem then, the area should be length times width. So I'm going to go 2x times 8 minus x squared. And I'll do this one by the product rule. And so I'm going to get 2 times 8 minus x squared plus 2x times a negative 2x. So that's going to give me 16 minus 2x squared minus 4x squared. So that's going to give me a prime is equal to 16 minus 6x squared. And then to set this thing equal to 0, I'm going to go 0 is equal to 16 minus 6x squared. So then negative 16 is equal to a negative 6x squared. X squared is equal to 16 over 6. And so I'm going to get x is equal to plus or minus 4 over square root of 6. Right? And we could rationalize it if we want. But again, with this problem, since we're looking to maximize, we're only going to care about the right corner, right? Whenever we're doing these problems, we only care about the right corner. So I'm going to test this at 4 over radical 6. If you wanted to clean that up, you could. It would come out to be 2 radical 2 over, 2 radical 6 over 3. But no matter. So this should give me a positive and then a negative if I plug into the derivative, and that gives me a local maximum, correct? And then in this problem, what are they asking for? I think again they're saying find the dimensions, so they want us to find the length and they want us to find the width. So let's go ahead and do that. So then the length of this thing is going to be 2x, correct? So then that is 2 times 4 radical 6, which will give me 8 radical 6. And if you want me to clean that up, I can. I'm going to get 4 over 3 radical 6. That's my length. And then my width, oops. Well, yeah, that's fine. That's my length. It doesn't matter. They're interchangeable. It's going to be 8 minus x squared. So then that's going to be 8 minus 4 over radical 6 squared, which is going to give me 8 minus 16 over 6, which will yield 16 over 3. So there's my width and my length. We okay with that? All right, cool. Now our last problem that we have for today is a doozy. This is the problem that I would have typically put on an exam had we had a in-class exam. So this is a problem that I think is important for you guys to know and understand. So please pay attention to it, because who knows, maybe we'll be back on campus. But if not, it's still good for you guys to know how to solve this problem. So this is an example of a biathlon. And so what's going on here is Ryan and Nick form a relay team. Ryan can swim at 4 miles per hour and Nick can run at 7 miles per hour. Ryan is dumped into the water 5 miles from a straight shoreline, where 12 miles from the closest point on the shore is the finish line. What distance x down the shoreline does Ryan need to swim so that Nick can run and to the finish line in the least amount of time? So in this problem, what we're trying to do is we're trying to minimize time. Okay, we're trying to minimize time. And so in order to be able to do this, this whole problem is going to be based off of this equation. Distance is equal to rate times time, but we need the equation in terms of time. So it's going to be distance divided by rate. Okay, that's the trick to this problem that most people epically mess up. Now I'm going to draw a picture of this problem for you guys so you guys can see it, and here's how it's going to look. So here's our shore, right? Nick is dropped off 5 miles from the shore. I know no, that's terrible. I'll just do it this way. I know that this distance is 12 miles, right? And we're trying to find out where the heck he should swim off to have where Ryan should swim so that Nick has the shortest distance to minimize time, right? So here's how we're going to do this. This is the x distance that they're talking about. What distance x down the shoreline does Ryan need to swim so that Nick can get to the finish line in the least amount of time? So if that's x, isn't the distance, the rest of the distance, isn't that 12 minus x? Correct? And since he's going perpendicular to a straight shore, we know that this distance over here is what this will be Ryan's swim. He'll swim 25 minus x squared distance in the water. Are you guys okay with the information that I've given you so far? Okay, so just to be consistent, this is Ryan's swim. This is Nick's run, right? That's their distances that they're going to cover, right? Now the problem that we need to do is going to be a time problem. So we're going to have time is equal to Ryan's swim, right? Ryan's swim time plus Nick's run time. Does that make sense? We want that to be the shortest thing possible. So if that's what we want, then what needs to happen is we need to write our things in terms of time. So I'm going to say, all right, time for Ryan's swim is going to be his distance divided by his rate plus Nick's distance, which is 12 minus x, over his rate. And this is the problem that we're going to use to minimize time. Do you guys see how this could be a tricky problem for people? Relating it to distance and rate for time. It gets tricky. Now, from here then what we need to do is we need to take the derivative, correct? So when we take the derivative, what we're going to do is we're going to go, okay, t prime is going to be equal to this guy's going to be, I'll write it down in pieces so you guys can see. 1/4, it'll be 1/2 square root of 25 minus x squared times a negative 2x minus 1/7. Are you guys okay with that? Let me clean that up. Actually, it's not very good. So I'm going to get a negative 2x. Oh, no, it's positive. Why am I going negative? Silly me. Positive 2x. We're going to have a 2 in the denominator. Ooh, this should be a plus. My bad, guys. I almost messed this all up. Okay. Are you guys okay with that derivative, or does anyone need me to explain it further? No, you're okay? All right, does everyone see how I use the Pythagorean theorem to get the 25 plus x squared under the square root? Okay, cool. If you guys notice I make a mistake, please correct me. I'm not perfect, and I don't want to mess you guys up, so it's important to me that you guys get this right. All right, so then t prime is going to be, the 2's will cancel, so I'm going to get x over 4 root of 25 plus x squared minus 1/7, right? But in order to be able to do this problem effectively and be able to analyze it correctly, we need everything under a common denominator. So then that means I'm going to get t prime is going to be equal to 7x minus 4 radical 25 plus x squared all over 28 radical 25 plus x squared. Are we okay with that? You all right? Okay. Now from here then, the denominator, you can see the denominator will never be 0, right? Because 25 plus x squared, you can't plug in any number that's going to make that become a 0. So we don't have to worry about the denominator at all. Again, we'll have to worry about the numerator. So I'm going to go 0 is equal to 7x minus 4 times the square root of 25 plus x squared, that quantity. Moving the 7x over, I'm going to get this. Then I'm going to get 7x over 4 is equal to the root of 25 plus x squared. I wanted to get the root by itself, because that way I can square both sides. I could have left the 4 there. That would have been fine too, but now I'm going to square both sides, so I'm going to get 49x squared over 16 is equal to 25 plus x squared. And what I'm going to do is I'm going to bring my squared terms together. Let me actually, I should have multiplied by the 16. It would have been easier to do. So let me multiply by the 16, just get rid of it. And actually, let me do this. It's cleaner if I don't move the 4 over. Squaring both sides there, I'm going to get 49x squared is equal to 16 times 25 plus x squared. Are you guys okay with that? And that's going to give me 49x squared is equal to 400, right? Because 16 quarters is $4. Plus 16x squared. Now bringing this 16 over, I'm going to get 33x squared is equal to 400. So x squared is equal to 400 divided by 33. X is equal to plus or minus the square root of 400 over 33. And since we're talking about distance is a positive. So we're going to only care about the positive number. And so we need to test that positive number. And so we're going to get 400 over 33. And you could have rationalized things. I don't care. It's not that big a deal. I'm going to get minus and positive. So that's going to give me a local minimum. And since I have a local minimum, that is the swim distance that will give me the shortest amount of time. Does that make sense to you guys? Are you guys okay with that? It's probably going to take you a couple times to watch this over, but now you'll be able to have these videos to watch over and over again. So if there's a question, you may want to just look at each example over and over again, okay? I'm going to stop the recording, and then if you guys have questions that you'd like me to do, I can go ahead and try and work on those questions for you, okay? All right, and